Let us discuss the solutions to assignment 3. Question number 1. Which of the following sequences converge to 0? You can assume all the basic properties of logarithms and exponentials that you have learnt in school. First, 1 by log n. Well, this certainly converges to 0 because, as you all know from school, as n becomes large, log n also becomes large. So 1 by log n will become small, and you can show that 1 by log n converges to 0. Problem number 2. 1 by n log n. Well, problem number 2 actually does not require any knowledge of logarithms. Just from the fact that 1 by n goes to 0 and the fact that log n will be greater than 1 if n is greater than some number, you can show that 1 by n log n goes to 0. 3. N by log n. This actually does not converge to 0, and it's slightly tricky to figure out why. What you do is the numerator n, you write it as e power log n. So this sequence becomes e power log n by log n. You already know that e power n by n, as n goes to infinity, does not converge. That is one of the things that we have shown in the notes, in the lectures. So similarly, with the same argument, you can show that e power log n by log n also does not go to 0 as n goes to infinity. Here you will have to use the property that log n converges to infinity, or rather diverges to infinity when n goes to infinity. For the final part, n by e power n log n, well, of course this goes to 0. This can be seen from what we have done in the exercises, that e power n by n converges to 0. Actually not in the exercises, I actually did it in the lectures. E power n by n goes to infinity, therefore n by e power n must converge to 0, and you can make this precise quite easily. Let's move on to problem number 2. Which of the following statements is true about the sequences an and bn? If an and bn are both convergent, then so is an plus bn. This is not true. What can happen is, for instance, you can take an to be the sequence n and bn to be the sequence minus n. Both sequences diverge, but an plus bn is a grand 0. If an and bn are both divergent, then an bn is also divergent. This is again not true, because you can consider, for instance, a sequence containing exponentials and powers. You can take both of them to be divergent, yet the product might be convergent. Okay, so think about this, why this is not true. You can cook up many examples. If an and an plus bn are both convergent, then bn is convergent. This is easily seen by subtracting an plus bn and an, and immediately you will get that bn is convergent. If an and bn are both convergent, then bn is convergent. This is actually not true. For instance, if you consider the sequence an to be minus 1 power n and bn, take an to be minus 1 power n and bn, or sorry about that, I got things a little bit messed up. Take an to be 1 by n and bn to be minus 1 power n. Then an converges, certainly 1 by n goes to 0. An bn also converges, but the bn does not converge because bn is minus 1 power n, which alternates between 1 and minus 1. Okay. Problem number 3. We say that a sequence an does not converge to L if. Now, here is the tricky bit. Many people have missed what this question is trying to say. The question is phrased exactly like how you will phrase a definition. So, what the question is asking is, which one of these, if you tick, will this become the definition of does not converge to L? Okay, now it turns out that several conditions actually imply that an does not converge to L, but only one of them, namely C, is the actual definition of an not converging to L. So this problem is not merely to get a sufficient condition for an not converging to L, but rather it is to give the definition of an does not converge to L. That's the way the statement is. We say that a sequence does not converge to L if this is exactly like how a definition is supposed to be, and only option C C is correct. The other options, for instance, if you looked at option A, for all epsilon greater than 0, for all n not greater in n, for all n greater than or equal to n naught, an minus L is greater than epsilon. No, that's not the thing. For a sequence not converging to L, you just need one epsilon for which the definition of convergence fails. So any statement that involves for all epsilon, you can immediately ignore. Now, why is option D wrong? Well, this says something grander. This says that there is some epsilon such that for all n after a particular point, mod an minus L is always greater than epsilon. That much is not needed. You just need there to be one n greater than n naught such that mod an minus L is greater than epsilon. You do not require the sequence to be always away from L for it to diverge. For it to not converge to L. You just require that no matter how far away in the sequence you go, there is always some point such that mod an minus L greater than epsilon. So only option C is correct. Now, question number 4. Suppose an is a sequence such that every rational number is enumerated by an. This just means that you have a sequence such that every rational number will eventually appear in the sequence. Such a sequence clearly exists because the rational numbers are countable, if you recall from week 1. Mark the true statements. It is impossible for an to be convergent. This is again obviously true because think about it. If an is convergent, an has to be bounded. Obviously, the rational numbers are unbounded. So, it's impossible for an to be convergent. It is possible for an to be convergent. Well, we have just said it's impossible for an to be convergent. Obviously, it's not possible. Some subsequence of an definitely converges. Yes, this is true because note that the numbers 1 by n are all elements that will occur in this an. Okay, an need not be 1 by n, but 1 by n will definitely occur. What you do is you just extract that subsequence such that the nkth element of this subsequence is nothing but 1 by k. That can easily be done. Okay, now one question you might have, what happens if let's say 1 by 2 comes after 1 by 3 in this enumeration an? It's not a problem. What you do is the following. Look at the first element 1 that occurs somewhere. Choose that to be the first element of the subsequence. Okay. Then look at half. If half has already occurred before 1 in an, ignore half. Then move on to 1 by 3. If 1 by 3 has already occurred before 1, ignore 1 by 3. Eventually you will end up with a number 1 by k that is coming after where 1 comes in the sequence a, and choose that to be the second element of the subsequence. Now proceed in this manner and you can show that this extracted subsequence will be a subsequence of 1 by k and therefore it will converge. Of course, we have said that some subsequence of an definitely converges, therefore it is possible that some subsequence of an converges. Again, this is all simple wordplay. Okay, now let's look at problem 5. Suppose an and bn are sequences such that an is equal to bn for infinitely many choices of n in n. Then if an converges, then bn converges. This is not true. For instance, look at the sequence 1 1 1 1 1 and look at the sequence minus 1 power n. Obviously, the second sequence does not converge whereas the first does, and they agree at infinitely many points. If an diverges, then bn diverges. Again, this is not true. You can just take an to be minus 1 power n and bn to be 1 1 1 1 1 1. An converges if and only if bn converges. No, that is not true. If an and bn are both convergent, then they both converge to the same limit. Yes, this is obviously true because an and bn agree at infinitely many values. It follows from the very definition of convergent that if both an and bn are convergent, then they must converge to the same limit. Problem number 6. This is going to follow from one of the exercises in the notes. This is to test your understanding of the behavior of the tail of a sequence. Let an be a sequence. For each fixed k in n, define the new sequence bn superscript k to be a k plus 1. So all we are doing is we are taking an and we are considering new sequences which are nothing but the sequence an, except you are starting from the term which is equal to k plus 1. Okay, so instead of starting at 1, you start plus k plus 1, and this sequence is called bn superscript k. Which one of the following statements are true? If bn is another sequence such that an is equal to bn for all but finitely many choices of n, then an is convergent if and only if bn is convergent. This is fairly easy to see. What is happening is we have two sequences an and bn which are agreeing with each other except for the first few terms. But in the definition of convergence, the first few terms is completely irrelevant. Therefore, an converges if and only if bn converges. If bnk is convergent for some choice of k, then an is also convergent. This follows immediately from a. Okay. C. If an is convergent, then so is each bnk. Again, this follows immediately from a. If an is divergent, then so is each bnk. Again, it follows immediately from a. So this sort of just depends on a. If you can show a rigorously, you are done. So let's move on to the next question. Which of the following requests are possible? A sequence that has no convergent subsequence. Well, this is easily possible. Just consider the sequence 1, 2, 3, 4, 5, 6, ... That has no subsequence that converges. Note, you might object and say, well, this sequence diverges to infinity. Yes, it diverges to infinity. Never say something like a sequence converges to infinity. That makes absolutely no sense. A sequence can diverge to infinity. It can never converge to infinity. A sequence that is divergent but such that every subsequence is convergent. Well, this is a contradiction in terms actually. If a sequence is convergent, then the trivial subsequence, that is the sequence itself, is also divergent. Therefore, this is simply not possible. A sequence such that for each real number r, there is some subsequence that converges to r. This is actually a bit tricky. This is nothing but that enumeration of the rational numbers. Okay, if you enumerate the rational numbers, you can actually get such a subsequence. It involves a bit of work. I don't want to go into this now, but it is a very, very fruitful exercise for you to try it out yourself, to actually construct a sequence using just rational numbers such that this happens. Okay. D. A sequence that has both a convergent and divergent subsequence. This is very, very easy to see that such things exist. Which of the following sequences are convergent? 1 by n squared and 1 by square root of n are obviously convergent. You have already seen this. Minus 1 power n plus 1 by n obviously does not converge. It oscillates. Unfortunately, there was an error in D. This actually does not converge, but unfortunately by an oversight, it turned out that I had marked it as correct. So some of you might lose a little bit of points. Well, it happens sometimes. I'm not going to go back and try to fix the scores for you. It's a negligible amount of score that you will lose if you had not marked this. So this one also sort of does not converge because this will also sort of oscillate. So it's an unfortunate error. Let's go on to problem number 9. Let an be a sequence that takes only integer values. Mark the true statements. If an converges, then the set an such that n in n is finite. Now this is a sequence that takes only integer values. If it has to converge, the only possibility is after a point it becomes a constant sequence. There is no other possibility. If it becomes a constant sequence after a particular point, the collection an will have to contain only finitely many terms. That is obvious to see. If the set an such that n in n is finite, then an converges. This is not true. You can just consider minus 1 power n. This just oscillates between 1 and minus 1. Therefore, the set will consist of just two elements, 1 and minus 1. Obviously, this is not, this is a finite set, but an does not converge. If n in n is infinite, then an diverges. Yes, this follows immediately from a. It is sort of like the contrapositive of a. Option D, if an diverges, then the set an such that n in n is infinite. Obviously, this is not true. We have already seen this in the earlier parts. Question number 10. What is the limit of the sequence e power n by n squared? We have already seen in the lectures that this is not a convergent sequence. Therefore, the correct option is D. The sequence is divergent. This concludes the discussion